Okay, let's see two specific examples of EAS reactions. They're both going to be halogenations. So how do we put a bromine or a chlorine on a benzene ring? So here is the first reaction we're going to look at. We're going to take chlorine. Now, in addition reactions, just adding chlorine to a pi bond, we will get an addition reaction to occur. Benzene rings are a lot less reactive. So, in addition to our chlorine, we need to add aluminum trichloride. You don't do this with a regular double bond, but you have to do it with a benzene ring. And the product here is going to be chlorinated benzene. Well, and that's our substitution. We replaced hydrogen with a chlorine. So how does this work? The first step involves the chlorine and aluminum trichloride. So chlorine is not reactive enough on its own to react with a benzene ring. So what happens is it attaches to aluminum trichloride. So one of the chlorine lone pairs binds to the aluminum, and aluminum doesn't have a full octet, and so by binding to the aluminum, we form this complex anion, or complex species. It actually contains a positive and a negative charge. Now, what to remember about things that have a positive charge? Atoms that bear a positive charge are telling you that they want electrons. And how do we give it those electrons? We're going to break a bond to that chlorine. So now, this is a super electrophile, the fabled super electrophile. And our benzene ring can then attack this chlorine, and in doing so, it's going to break this chlorine-chlorine bond and give those electrons to the atom that's asking for them, that chlorine with a positive charge. That gets us to this structure, our unstable, not aromatic carbocation intermediate, and then we'll have some base in here. There's going to be something. Sometimes your base is arguably oxygens on the wall of your glass flask. So there's going to be a base that will remove this hydrogen and reform our pi bond. Again, this is a carbocation intermediate. What happens to carbocations? They either get attacked or they lose a beta hydrogen. So here we're going to lose a beta hydrogen. We're going to reform our double bond and restore aromaticity. So here's our mechanism, and here's our overall reaction. There's another reaction. It's bromination. It looks very similar. Instead of treating with Cl2, we'll treat with Br2. And in this case, we're going to treat with iron tribromide instead of aluminum trichloride. These are just, it's a different match set for doing a bromination. But the end result is the same. We get substitution on a benzene ring. In this case, we put on a bromine. Now, the active electrophile is a little bit different. Instead, but it looks, it's the exact same process. We have Br2. Br2 reacts with iron tribromide. Looks a whole lot like this did. And we form another super electrophile. Positive charge, negative charge, and this now is what the benzene reacts with in the bromination. So here's our super electrophile. And you can fill in the blanks and complete that mechanism. But these are two very simple electrophilic aromatic substitutions. They follow the exact mechanism that we talked about in a previous one to achieve substitution on an aromatic ring.